Welcome to Hyperstition episode number 7, Quantized Inertia. A topic that's come up online a lot recently has been the stagnation and fundamentally new theories of physics. And a lot of this has been frustration with the research paradigm of quantum gravity. People saying, we need to figure out quantum gravity. That's the holy grail. And it may be missing things that are hiding in plain sight. And some context for that is that really Albert Einstein was just such a genius. You know, people have taken Einsteinian general relativity as sort of sacred in some sense and saying everything that comes after has to fit in that context. And so we make observations in cosmology or astronomy, things like the rotation curve of the galaxy showing orbits of stars further out from the core that are a lot faster than they should be, thinking, well, Einstein has to be right, so there must be mass we just can't see. There must be dark matter. And Einstein, he called it his greatest blunder, was including a cosmological constant in the Einstein field equations. That was initially an expansionary effect to counteract what would normally happen, which is the universe would be collapsing under its own gravitational weight. And this cosmological constant has now been revived through observations of distant supernovae showing the universe is accelerating and that, or it's expanding, and that rate of expansion is accelerating. But even this inflationary, it's called lambda cold dark matter cosmology. Even this inflationary view of cosmology is starting to face observational evidence that is difficult to square in an apparently different rate of expansion over time that doesn't exactly agree. And so dark matter, dark energy, cosmological inflation, ultimately, these are kind of, to some extent, parameters that we use to fit our observed facts with Einstein's general relativity. So did Einstein actually have the last word on theories of gravity? And is there anything beyond Einstein's general relativity? Well, it is difficult to challenge these things in such an established paradigm. And as Eric Weinstein and others have pointed out, like Sabine Hosfender as well, you know, the scientific literature is very politicized. It's very difficult to push through new theories that challenge the status quo. Even Thomas Kuhn wrote about this in The Structure of Scientific Revolutions, that every generation of scientists becomes very dogmatic about the things they believe to be true. And so our guest today is, I think, a truly contrarian and original thinker, someone bold enough to challenge the existing paradigm and propose not just new theories to modify gravity, but also ways of experimentally testing them. So I'm very excited to bring up on stage here Dr. Mike McCulloch. Mike McCulloch is a professor of physics, formerly at Plymouth University, and I believe now is an independent researcher, kind of gone rogue, you know, fully divorced from the establishment, which I have huge respect for. So, Mike, thanks so much for joining us. And I'm curious, you know, kind of what are you working on? What is your focus these days?
Well, thanks so much for inviting me on your show. Yeah, and I agree with what you said, that physics has become locked in a cycle. So I'm trying to suggest an alternative kind of physics that is more testable and more successful as well. So I've prepared some slides to explain that physics, and in an accessible manner, I hope, and show you that when you do regard physics or approach physics in a more testable, intuitive way, it automatically produces applications for that physics. It makes it useful. So that's the second part of the talk.
Awesome. And I mean, physics is upstream of all technology, really. I think it's like basically what we can even imagine is bound about what we think is physically possible when it comes to like developing new technology. So this is exciting because right here you have the possibility of reactionless thrust, which would revolutionize everything to do with aerospace and space travel forever. So let's dig in. I think I'm really curious to learn more about what quantized inertia is claiming and where it matches our observed evidence.
Okay, yes, and feel free to ask questions as I go along and interrupt me.
Sure.
So the opening slide, well, it's just an opening slide, really. It shows what may be possible with this sort of technology. An image from Rogue One, of course, a very good film. But in the talk, I'm going to try and talk about what inertia has been assumed to be. The new theory I'm suggesting, which is quantized inertia, show the evidence for it, show how it produces reactionless thrust, the evidence for that, and then how we may be able to get things like quantum launch and interstellar travel from it. So I shall now go to slide 2. So I guess I don't know if I should go through my background.
Sure.
but
No, I think it'd be good context.
I've got the usual BSc in physics, York, 1991, PhD in ocean physics. I which is a more testable kind of physics. I came up through a different pathway than most, I think, that way. Then I was an ocean wave scientist at the Met Office in the UK for about 10 years, working on the ocean and wave modeling as well, which helped. And then I was a lecturer in geomatics at Plymouth University in the UK. And as you say, I'm now independent and crowdfunded. And over the past 20 years, I've been suggesting this theory. And I published 28 papers on it and four books. The books you can see here. So this is the latest one. Okay, so yes, I guess this isn't going to actually run. But what this is supposed to show is a lorry coming along with a ladder on top, hitting a car, stopping, and the ladder continues onwards. And this is the usual idea of Galilean Newtonian inertia, that objects keep going at constant speed unless you force them to stop. But this, to me, has never been an adequate explanation for inertial mass. It's almost just words. It's based on what we're used to, watching balls rolling on flat surfaces and that sort of thing. And it's never been understood why things should keep going in a straight line. So I decided to think about that and try to model it in an intuitive way. So I've proposed the first model for inertial mass, which is shown on the next slide. So in this slide, you can see the black ball in the center. Well, that is supposed to be accelerating to the right. And according to quantum mechanics, every time something accelerates, it sees a kind of radiation which is now called Unruh radiation, actually pointed out by Fulling Davis and Unruh back in 1976. And I've shown it on this slide with a red color, but it's not actually showing the entire slide. So you have to assume that the green here, the slide is not all visible, or the color's not right. Anyway, this green shows that there's more Unruh radiation in this area than in the blue area. And Unruh radiation has actually been seen by, oh, that's better. Yeah. Okay. Yeah, very good. So, although it's still not showing red, but never mind. So this green is Unruh radiation, and it's been seen by Lynch et al. So if I show the next slide, yeah, the colors are slightly different. So Unruh radiation was confirmed in 2021. So Lynch looked at data on positrons decelerating in silicon crystals, shown in this sort of box here with the blue and the red. The positrons hit the silicon crystal, decelerated very fast, and released a radiation which looked exactly like Unruh radiation. And the spectrum of it is shown on the right-hand side, and you can see that the curves agree. So this looks exactly like Unruh radiation. So this radiation has been seen, and they published it in this experiment, this paper down here at the bottom, experimental observation of acceleration-induced thermality. So we have
question on Unruh radiation. This is really normally we have this expectation that all observers should kind of observe the same physics or have some agreement of observations, right? But that's true.
Yeah.
This Galilean invariance, which is if two observers are only separated by a difference in constant velocity, then they should experience with the same. We don't know from first principles or ab initio what velocity we're traveling at. But Unruh had this claim around, well, and is this related to the quantum vacuum, where as I accelerate, I perceive the quantum vacuum as having some kind of distinct finite temperature that depends on the acceleration?
It does, yes. It's somewhat cyclical, but you can say that if you're accelerating, you will see a horizon. And I actually show this in the diagram here. On the left of the ball, there's a black area, which is beyond the horizon, because information from that black area will never catch up to the accelerating object, because speed is limited to the speed of light. And what this this horizon does to the quantum vacuum is it splits virtual particles, which are appearing all over the place, and they usually recombine very quickly. But with a horizon, as in a black hole, if you have two particles emitted on the horizon, one goes behind and is lost to the observer, and the other one comes out and becomes real because it can no longer recombine. So this is why you get Unruh radiation. It's equivalent to Hawking radiation in a black hole, but just for accelerations.
Right. And that's called a Rindler horizon. Is that right?
It is, yes, that's right.
Yeah.
So the horizon is shown here on the plot. So we have this radiation and we have the horizon. The new proposal I'm making is that this horizon damps the radiation. So it's acting almost like a metal plate in which the electrons can move to cancel the electromagnetic field. So to the left of the ball, the black ball, the Unruh radiation is being damped. It can't exist. Certain waves can't exist between the object and the horizon. They're being damped by them. So that means that you've got more radiation in front, less behind. So you've got more radiation pressure on the ball from in front than behind. So it tends to get pushed back against its acceleration. And I managed to show in a paper in 2013 that this looks like what we know as inertial mass. Every time something accelerates, it sees the Unruh radiation, the horizon, which makes it asymmetric, and it gets pushed back against that acceleration. And it agrees very well with what we know as inertial mass.
Okay, interesting. So the resistance to being accelerated is something we think of as inertia, but really that's the radiation imbalance between the forwards and the backwards direction created by this Rindler horizon, which is an artifact of acceleration.
Yeah, that's exactly right. Yes. So inertial mass doesn't exist as an intrinsic property of a body. It's more like an interaction between the body and everything else in the universe.
Interesting. I mean, there's this question in my mind too, which is like inertial mass happens to be the same as gravitational mass, but I don't know if that's, is that are we kind of getting into that?
So strictly, this violates what's known as the equivalence principle, where Einstein, of course, assumed that inertial mass is exactly equal to the gravitational mass. But when you work out the maths for it, you see that it does it in such a way that's independent of the mass itself. It's like an extra constant term for the inertial mass. So if you go back to Galileo and he's dropping two balls of different mass off the Tower of Pisa, or whatever he was doing back then to test it, then the balls would still fall together, even with this new model of inertia, because this extra acceleration, this different acceleration, is independent of the mass. And most of the torsion balance experiments, well, all of them that they use to test the equivalence principle are of this form. They're effectively measuring two balls falling with respect to distant galaxies. So it doesn't violate any data sets. That's what I'm trying to say.
Mm-hmm.
And I'll talk about gravitational mass in a minute as well, because I have something to say about that.
Interesting. I thought the Einstein equivalence principle, I thought the equivalence was really more the equivalence between like straightforward acceleration, what we think of as movement through space, that acceleration is equivalent to being close to a gravitational body, the acceleration you feel from gravity. But does that imply that, I guess that implies inertial mass is the same as gravitational mass?
Yes, it does. But what I'm going to say is that they're very slightly different.
Okay.
And it's a very slight change, as you'll see. It's absolutely tiny. You only notice it if it's in deep space.
Okay, right. And in this framing, if I was just feeling acceleration from gravitational mass, I would not see this Unruh radiation.
So the two effects would cancel, and that's a very interesting question, because the two fields, the two Unruh, the gradients in the two Unruh fields, I suppose, would cancel, and so you would have no force on you. So you would get back to Einstein's most beautiful thought that a falling man doesn't feel any sensation.
Mm-hmm. Okay, yeah, I think I'm following so far.
Okay, so, but there is a slight amendment to this, and this is what fixes things like galaxy rotation and that sort of thing. So if we look at the entire universe, so this white ball in the center is supposed to represent the universe, and at the bottom within the white unit cosmos, we have a rocket accelerating very fast. So you can see the black arrow and the orange flame coming out of it. So it's accelerating fast. It sees Unruh waves which are relatively short, because fast accelerations mean short Unruh waves. And of course, they're all towards the front of it because it's got a horizon behind it that damps them. So it sees a pushback, so it has inertial mass as we expect. But there's another rocket above it towards the top of the white area, which is accelerating very slowly. Its rocket's almost off. So it's got a very low acceleration, so it sees very long Unruh waves. And if it's accelerating slowly enough, the Unruh waves will be too big to fit inside the cosmic horizon. And at that point, they will not be able to exist. So I like the philosophies of Ernest Mach. I tend to follow them to the extreme, and if you can't observe something, then it's a good idea in physics to assume that they do not exist if you can't, in principle, observe them. So I'm saying that very long Unruh waves would not be observable, and therefore they don't exist. They can't fit within the universe, if you like.
This is the kind of this classic, like the boundary conditions in physics. It's like same with like the Casimir effect, where electromagnetic modes that cannot fit between the two plates create this kind of apparent negative pressure such that the plates feel this force coming together. In this case, it's more in front of the object. Unruh waves of a super long wavelength can't fit in the observable universe, and so you would see, I guess, a little bit less decelerating force than otherwise.
Yes, that's right. Yeah, so the inertial mechanism I just told you about, the asymmetry, is slightly reduced by the cosmic horizon because it damps the waves a little bit on the forward side as well. So what it means is that very low acceleration should have less inertial mass than we expect.
What's the sort of scale of this effect? Like how big, like what order of magnitude kind of numbers to get intuition for?
So it produces, well, as I'll show in a minute, it produces a minimum acceleration of about 2 times 10 to the minus 10 meters per second.
Okay.
Which is very, very small. So
yeah, 10 orders of magnitude, I mean, less than gravity, pretty much. On the surface of the Earth. Yeah.
Yes.
Okay.
Although, as I'll show in the second half of the talk, I think, well, I'm sure there are ways to enhance that hugely, but that's something to come. That's the propulsion bit.
Yeah.
Okay, so we can derive this. So there are two nice ways to derive it. So I don't know if you want me to go into how deep you want me to go into the maths.
Yeah, I mean, let's take a quick tour through, and it'd be great. I'll try to help translate for the less mathematically inclined.
Okay, yeah, I wasn't sure whether to include it, but the diagram shows, the colored diagram, the square rectangle, shows a Planck mass within a cosmos, square one, just for simplicity. So the Planck mass is a square in the center, and it's got a Rindler horizon on its left because it's accelerating to the right. And it's got a cosmic horizon way off to the right as well, as you can see there. So, and now if you consider Heisenberg's uncertainty principle, so this is where I start, you can see at the top left is Heisenberg's uncertainty principle. So dp dx is h bar over 2. So the uncertainty in momentum times the uncertainty in position has always got to be more than a very small number, Planck's constant. So if you look back at the picture, you can see that on the left side of the accelerating Planck mass, the Rindler horizon is close, because Rindler horizons are much closer than the cosmic horizon. So the uncertainty in position is small, relatively small. It's actually c squared over the acceleration, but that doesn't matter so much. But on the other side, the distance to the cosmic horizon is huge, So the uncertainty in position on that side is massive. So because it's a reciprocal between the momentum and the position in Heisenberg's uncertainty principle, whenever you have a large uncertainty in position, you have a small uncertainty momentum. So that's why I've shown the red arrow pointing to the right in a rectangle as small, and the uncertainty momentum the other way is large towards the Windler horizon. So this is how Heisenberg's uncertainty principle predicts the force on a Planck mass due to the Windler horizon and the cosmic horizon. It predicts that the object is going to move back towards the Windler horizon, which is just what I said before with the other schematic. It's the same thing, but this does it quantitatively, because if you look at the maths, and I guess I will if you want, but I won't go into detail, but you can see that what you get is a formula which is not there, apparently, which is, I wonder if I can show you the next slide. Yeah, some other formulae are not appearing, which is not good. But the equation should look like this. This is what you get. So you get that the modified inertial mass is equal to the original one we all know about, which is equal to the gravitational mass, times this factor. So it's 1 minus c squared over the acceleration of the object times the cosmic diameter. So that's what the formula looks like. So I'll now go back again to this. Yeah, it's a shame that the equation's not showing up. They do in my copy, but sorry about that.
That's okay. So, but the intuition here is really that, okay, so as an observer is accelerating forward, they have this apparent Windler horizon that forms behind them, and that gets closer the faster they're accelerating. Now, the cosmic horizon in the distance in the front is fixed, but you're saying that because the Windler horizon is closer behind us, that means that that corresponds to a more definite position. So our uncertainty momentum behind us is larger than the uncertainty momentum behind in front of us, and you're saying that manifests or appears as a decelerating force.
Yes, that's right. So statistically, the random quantum force, if you like, will more often be backwards towards the Windler horizon than it will be forwards.
Right.
And so you'll get an inertia-like force, which is exactly like inertia.
I see. If I think of these two uncertainties and momentums as like random number generators, and behind me, the numbers can be larger than the ones in front of me. And so if I add them up constantly, I'll constantly get a kind of bias towards my behind.
Yes, that's right. Yeah.
Yeah. Yeah.
And there's another way to do it, but it's also disappeared. So I can't show you that one. But there's another way to derive it. I can show you the diagram actually, which is shown here. So if the object is this black dashed line here on the sort of top right, before it accelerates, it can see all the way to the cosmic horizon. So I've shown all these green dots going all the way to the cosmic horizon. And I'm assuming here that 1 bit of information is 1 green dot. Now it accelerates to the left, and suddenly it sees a Windler horizon there, which is the blue line. And now it can only see the purple dots. It can't see as many dots as it has before, so it's lost some information. And according to Landauer, every time you lose a bit of information, you gain a certain amount of energy, which I show in this derivation, but the equations don't appear for some reason on this. And so if you calculate the energy that's released by these dots which are hidden behind the horizon, the energy you get out is exactly equal to the energy you need to produce the formula I just showed you, the one where the inertial mass is almost the same as the inertial mass in F equals ma, but it's got a slight difference caused by the cosmic horizon. So again, you get if I can show you this formula again, you get this formula. The one at the top, you can derive the same formula using information theory. So I've derived it 2 different ways, just in case you didn't believe the first one.
That's good. This kind of connects to this, like Verland has this entropic theory of gravity, where gravitational forces are emergent from entropy, or a kind of information argument as to why we observe gravity, and that this would kind of reproduce Einstein's field equations, but coming from this purely information, I guess, theory perspective.
Yes, although that's a bit different. He's looking at gravity, and I'm looking at inertia. But
right. Okay. So, so we're losing bits behind us. So it means that there's less energy behind us, or it means that by losing those bits, we have dissipated energy in the form of entropy. Like entropy is energy at a certain temperature, right?
Yes, you're right. As we lose the bits behind us, then that would imply that entropy goes down because we've lost information about the universe. But that can't be allowed. So heat must be released to counter that. And the heat that's released is the unruh radiation that I've just been talking about.
Right. And that I think that connects to this idea in black hole thermodynamics, where things that fall past the event horizon seem like they're losing entropy, or seem like they're losing information. Now, there's some people that have claimed to resolve this. Leonard Susskind and Juan Maldacena, they're cool horizons for entangled black holes. They say that, well, information is perhaps stored as entangled Hawking radiation at the boundary, which we would see as a kind of temperature. So it's a similar argument here, where we're losing information past the horizon, but it would show up as a temperature that is finite and measurable as entangled radiation. You mentioned these virtual pair production.
Yes, that's right. And I think in black holes, information is destroyed and it's emitted as heat.
Right.
That would be my take on that. Okay, so with this equation for inertial mass, which again isn't appearing on here, but should be, but I've shown you it anyway. So this helps us, well, it enables us to solve the galaxy rotation problem very, very simply. So here's a galaxy. This is the Andromeda galaxy. Stars are orbiting around it. And in the center, everything's fine. They don't need dark matter. It obeys Newtonian laws. But at the edge, stars are accelerating very slowly. And it turns out they're moving far too fast, so that the centrifugal force should be huge on them, pushing them out. But there isn't enough, as you know, visible mass to gravitationally bind them to the galaxy. So they have to add lots of dark matter to the galaxy to make it all work out in general relativity. But what quantized inertia does for you is that when accelerations are low, it reduces the inertial mass. And it turns out that when you model a galaxy, it reduces the inertial mass and the centrifugal force by exactly the right amount that you don't need any dark matter at all. So you can see that the centrifugal force there has a long arrow and a short arrow. It reduces the long arrow to the short arrow, so it balances the gravitational force exactly. And it's a very simple equation, as I showed. I can show you it again just to show you how simple it is. It's shown here at the top, and the only parameters are the speed of light, the acceleration of the stars, and the cosmic diameter, and all of those are known. So there's no fudging. There can be no tuning of it. It has one chance to work, and it does.
I mean, and I think that's what stood out to me when I first read some of your papers was explaining the galactic rotation curves without introducing kind of more free parameters, right? That are sort of experimental fit parameters.
Yeah.
You know, von Neumann had this quote, like the exact details, but it's like, give me 3 parameters, and I can draw an elephant and give me a 4th, and I can make it like wiggle its tail, right?
Yes, that's exactly right. Yes, I really hate adjustable parameters, so I refuse to use them.
Okay, so we have this argument as to why we should see reduced inertia based on the allowable wavelengths of unruh radiation that can fit between the Rindler horizon behind us, formed by acceleration, and the cosmic horizon ahead of us. So in this sense, so why these stars aren't flying out into space is because they experience this centripetal acceleration. So they have this Rindler horizon approaching from behind, and then they experience more radiation pressure from from the outward direction, and that kind of keeps them confined in these orbits. Is that a correct understanding?
Well, it's subtle. It means that for these edge stars, the Rindler horizon is almost as far behind them as the cosmic horizon is in front.
Hmm.
And the Unruh waves are so long that they're being damped from all directions equally by the cosmic horizon. So the inertial mechanism just doesn't work. This doesn't work anymore because the Rindler horizon is nearly as far away as the cosmic horizon. So they feel like they're in a sphere, and there's no asymmetry, but much less asymmetry. So
Okay. I'm
so
trying to
inertia becomes less efficient.
Well, so this is the thing. I guess why in that case, why would stars further out from the center of the galaxy feel more of a corrective force than ones on the inside if they all effectively view the same working, I guess, same allowable diameter for these I guess, momentum waves or these Unruh waves?
That's a good question. So I can take you back to this slide. Yeah, this one. So the bottom rocket sees short Unruh waves, which are damped on one side by the horizon, but not on the other side by the cosmic horizon because they're short enough to fit. But the rocket above is accelerating so slowly that the only Unruh waves it sees are extremely long. And they're all, or most of them, damped by the cosmic horizon, which works on both sides. So there's no asymmetry there. So therefore, there's no inertial mass. And therefore, there's less centrifugal force, the inertial force.
Oh, okay. I think I get it. So this is okay. So this is, yeah. So at very low accelerations, you have very long Unruh wavelengths. Those are the ones that get damped. And so
yes, that's right. Yeah, by the whole cosmos symmetrically.
Right. Like they can't fit inside the boundary conditions of the universe. Okay. And so basically, this galactic rotation curve anomaly is really assuming that their gravitational mass is the same as their inertial mass, which is not true because at low accelerations, you would measure a lower inertial mass according to the equation you provided that you kind of derive two different ways. And so those stars, so there's enough mass in the galaxy that we can perceive to account for them being confined in these orbits at larger distances at higher velocities.
Yes, that's right. Yeah.
Okay. Interesting.
Yeah.
Okay, and so where do we go from here then?
Okay. Well, I was going to talk a little bit more about empirical proof before I get onto the
yeah, please do. Yeah, this is great.
Proportion bit, because I mean the theory does sound quite esoteric when I start talking about cosmic diameters and things like that, but the proof is incontrovertible. I mean, I suppose I would say that, but as I'm going to show you, it's very strong indeed. So this is a paper I published just showing how the theory predicts a lot of the galaxies that we see out there. So this is data taken from the Spark catalog, from Stacy McGough's catalog, and there are 153 of them. And here I've plotted expected acceleration, so the expected spin, if you like, of the galaxies along the x-axis, and the observed acceleration along the y-axis. And the grey squares show the data, and you can see that at the bottom there's more observed acceleration than you would expect. So if the observed was as they expected, they'd all be along the dotted line, but they've risen above the dotted line at the bottom for low acceleration. And this is the galaxy rotation problem that shows they're orbiting too fast for low accelerations. The quantized inertia prediction is shown by the dashed line, which agrees with the data very well, as you can see. And there's also another theory called MOND, modified Newtonian dynamics, which is shown by the solid line. But MOND isn't as good because it has an adjustable parameter in it, A0. QI agrees very well with MOND, but it predicts A0. It doesn't need A0. So It's better in that way. So I published this in 2017.
And what has been the reaction of the academic community when you've kind of presented these ideas or brought them up? And you'd think being able to explain this galactic rotation curve issue without introducing dark matter, without introducing any kind of fit parameters, you'd think this would be a popular thing. You'd think people would jump on it.
Yes, I was expecting it to be more popular than it is. I guess the problem is that I'm throwing away a lot of baggage. I mean, as you said at the beginning, very wisely, the way people work these days is to use the basis of general relativity, so metrics, curve space, that sort of thing. And partly because of my philosophy, I've rejected that because I don't want to build a physics on something that can't be directly tested. Because with curved space, you can see the effects by passing something through it, and you can see it bending, but you can't actually measure the curved space itself. You can't test the mechanism of it. Whereas with what I'm suggesting is a variation of the quantum background in space, gradients in it, and that predicts the same thing that the curved space does. But with what I'm suggesting, you can test it because you can measure the quantum vacuum at each point, and you can see that it's changed. You could use a Casimir probe, for example, measure the Casimir effect at different locations, which would be hard, but not impossible. So I think this is much better.
Let me push back for just a second there, because I think, there's this line I've heard a million times, as a student in physics and ever since, but that Einstein's theory of relativity or general relativity is one of the most, rigorously tested theories ever in history. And, it's not just sort of, GPS clocks and stuff like that in orbit that experience some time dilation effect, but also the curvature of light as it bends around supermassive objects in deep space that shows that light geodesics follow this least time path, and that this ends up having what we see as a curved path because of the curvature of space-time. So are you saying that what we measure as apparent curvature is kind of an artifact of something else?
Yes. So quantized inertia also predicts lensing, the bending of light around galaxies, and it also predicts the bending of light around the sun, just as general relativity does. But I think this is not mentioned often enough, that general relativity, and you might get a shock from this, but has been falsified by every single galaxy that we've ever seen, because it predicted the orbital speed and it got it about 6 or 7 times wrong. So of course, they've added dark matter to make it fit, but that's not what happened in the beginning, and they don't talk about that. So I don't think it's true that general relativity is the best tested theory out there. I think it's got a crutch, which is dark matter, which is helping it.
Yeah, it's a good point, and that's kind of, I mentioned this beginning. It's kind of an epistemological trap. It's like if you say this theory must be true, and now we have to kind of add epicycles, right, to the theory to keep it correct in the in the free parameters. First we'll have free parameters for dark matter, and then we'll add some for cosmological inflation that maybe now changes as a function of time and have different inflation rates in different periods of time. I think I kind of see where you're going. So Einstein has been very good at predicting a whole lot of things. Does not actually predict galactic rotation curves. And so it's not complete in that sense. There's missing elements in some sense.
That's right. I think it's fine at high acceleration, so within the solar system, near the sun. But whenever you get to deep space, it falls down.
And okay, so does quantized inertia then also help us approach this larger scale of like this, what we see as an accelerating expansion of the universe, or and that is from these distant supernova explosions that look like they have an increasing redshift with distance, faster than just a constant acceleration. So rather the speed of acceleration, or sorry, the speed of inflation is also increasing, and we call that responsible for dark energy. And so does quantized inertia also let us approach this? I think dark matter and dark energy are the two big, missing elements in
It predicts it exactly. I've got a slide on that. and I think the maths is okay on that slide. I could. Shall I go forward to that one? I'll just.
Yeah, sure, as you like.
So, yeah. So this slide shows the modified inertial mass, which is mi, regards to the unmodified one, which is mg, and this factor I've been talking about. So if you put this new inertial mass into Newton's second law and gravity law, so you can see that on the second line there. So mi is replaced by the more complex term I've shown above. Then what you get is the bottom formula, which is a equals gm over r squared. So that's a familiar one, the acceleration due to a gravitational mass. And then you get this extra term out, which is 2c squared over theta, where c squared is, of course, speed of light, and theta is a cosmic diameter. And this term, when you calculate it, because those numbers are known, comes out at 2 times 10 to the minus 10 meters per second. It's acceleration, of course, and that is the cosmic acceleration. That's the acceleration of the cosmos at its edge. So it predicts it exactly. And this is you can see that even if the gravitational mass is tiny or zero even, you still get this residual minimum acceleration, which has to exist everywhere. And the prediction of the theory is that there can be no acceleration lower than that, because then the under waves would be longer than the cosmos and would be unobservable.
Is that, I'm curious if that like kind of order of magnitude acceleration is within sort of experimental reach. I know there's ways of measuring small deviations in Earth's gravity using like gravimetric sensing, which is, I think, based on the interference of two particles that have some, like the de Broglie relationship between their size and momentum. You can have them interfering in such a way as to measure very, very tiny variations in even the Earth's surface gravity. People want to use this for like mineral exploration, that kind of stuff. Is this kind of size of acceleration something that we could see as quantized?
As far as I know, it's pretty much unobservable on the Earth, because there's so much going on where the acceleration is larger. So it's quite hard to see, except in that the great thing about having, well, the cosmic diameter in there, there's this theta on the bottom, this Greek symbol, is that it predicts that the effect is boosted if you have a small cavity. So instead of having the cosmic horizon, what if we had a small cavity? That would hugely boost this acceleration. And I'll, in the second part of the talk, I'll talk about the thrusts that have been seen because of this. So I think it is observable if you sneakily reduce the cosmic diameter to make it bigger.
Well, I'm curious about that. I mean, for electromagnetic waves, I know that, you know, we can force a boundary condition because a conducting plate has the E field at 0 in the idealized case, but it's because there's charges rearranging themselves on the surface to cancel out the imposed E field. And so that's why this Casimir effect, you can have electromagnetic wavelengths that can't fit inside this, similar to like a string instrument. You know, it's like the frequency is determined by having the fixed boundary conditions the string can't oscillate at. For this case, though, what is the physical intuition, or what is the physical mechanism that establishes the boundary condition for these? I'm going to call them momentum waves. I don't know if that's incorrect.
Yeah, so it's something I call a hard horizon. So for any horizon, you, by definition, you can't see behind it. That's what a horizon means. So if you had a partial wave that goes through the horizon and isn't 0 on the horizon, then you would be able to determine that there is something behind that horizon. So it won't be a horizon anymore. So if you're going to have a horizon, you've got to make it absolute. So you can't have any waves going through it. They have to all be 0 on that horizon. So that's the kind of philosophy I use to
okay.
Yeah, if that makes sense.
Yeah, well, I get the concept of a horizon in that sense, but what is physically what creates, I mean, in this, so the Rindler horizon is this apparent region from which information cannot reach us. It's like a hard boundary in that sense, like no information. So long as we accept, I guess, the speed of light is a fixed speed of causality in some sense. And then same with like the cosmic horizon, like there's no information coming from outside our universe, I guess. How do we construct a horizon from which no information can reach us? Like physically, like in an engineering sense?
Yes, well, as I'll show you, I think a metal plate is enough because a large proponent of the Unruh radiation is electromagnetic.
Hmm.
And the reason I could say that is because of the results we've had. So it seems that a large component of Unruh radiation is electromagnetic. So it seems to work anyway.
Mm-hmm. Okay.
So if I just go back a few, so I was on that one. You can also get gravity from this kind of thing. So this shows a planet in orbit around a star on the right-hand side. And it's a similar argument to the one I had before. Between the planet and the star, there's a lower position uncertainty. So dx is small, and I've shown a small dx there. Between the planet and the cosmic horizon, there's a large position uncertainty, so I've made dx big. And again, with Heisenberg's uncertainty principle, you can take the reciprocals with momentum. So you can say that the momentum uncertainty is greater towards the star. So the planet will be attracted to the star. And it turns out that if you do the maths, you can, I did this in 2014, you can predict the, well, it's not actually shown there, but what's supposed to be there is Newton's gravity law. So at the bottom there, so it should be F equals GMM over R squared. And I published that in that paper there. So you can get gravity out of this sort of thinking as well.
Okay, I'm trying to see if there's like, the feel that there might be something circular here, because you're saying this effect is produced by these small scale accelerations, but in this normal GR perspective, the acceleration itself is because space-time is curved, and that's why things are drawn towards the star in the first place. So if you're saying we don't get, if you're saying the space-time curvature is sort of an artifact of something, then what provides the initial acceleration towards the star in the first place?
So you could think of it as a kind of sheltering, I suppose. The Unruh radiation is being sheltered between the planet and the star.
Oh, okay. So the star is acting as one side of the boundary condition. The other boundary on the outside is the cosmic, the cosmic boundary itself, right? Yes,
that's right. And this is working at the quantum level. So it's between Planck masses. All the Planck masses in the planet are interacting with the Planck masses in the star. And the quantum waves are being damped between them. That's the only way the maths works out. If you assume, excuse me, Planck masses.
Okay, I think I'm following.
Yeah, okay. So next slide. And just to prove that this has to be quantized inertia and Unruh radiation, this is perhaps the best proof I can show. So this yellow thing is a galaxy orbiting. In the center, the accelerations are very high. So you can see the dotted line taking you down below to show short Unruh waves. So it's these short Unruh waves, and they're fine because they're not damped much by the cosmic horizon, which is very far away. They fit within it. And then as you go to greater and greater radii, the acceleration reduces. So the second white dotted line downwards shows, ends up in longer Unruh waves, this red curve. And at exactly the radius at which these waves get to the cosmic diameter's size, that is the radius that galactic behavior deviates from the Newtonian and becomes obeys quantized inertia instead at that exact radius. So that proves very specifically that it's Unruh radiation that is responsible, and probably quantized inertia as well.
So I'm trying to think about this. So if stars can act as effective boundaries that kind of limit these inertia modes or these Unruh modes, then I mean, there's constantly things passing between our star and the center of the galaxy or other stars. So would we not see some kind of like variation in this sense? Like when something passes behind us, oh, I guess that we just see that as normal gravity. It passes behind us, we feel
Yes,
more attraction towards it, and then it passes, you know?
yeah, it looked like gravity. Yeah.
Yeah, yeah. Okay, okay. Hmm. Okay, so I think we got a handle on this galactic rotation problem where the curves can be better explained or more accurately predicted, I guess, from first principles using this kind of mental model where inertia takes on quantized values based on the horizons on either side of the object. And if the horizon is shorter towards us, we feel more force towards that. But now,
Yeah.
can we also get to this problem of like cosmological inflation and dark energy?
Yes. Okay. So I've already shown you the slide where QI predicts. Where is it? Yeah, this one. So QI predicts very simply the cosmic acceleration, which is simply that term you get left up with at the bottom, the 2c squared over theta. And the value of that term, if you put the values in, you'll see it's 2 times 10 to the minus 10 meters per second, which is the cosmic acceleration at the edge of the cosmos. So that all fits very nicely. The problem I have, and this is one of the things that's controversial about it, is that it means Newton's first law is no longer quite valid. It's a very slight change. I mean, the acceleration is tiny, but it means Newton's first law that says that things go in a straight line at constant speed, that can't happen anymore. In a quantized inertia model, you can't have that because a constant speed would mean infinitely long Unruh waves, and they wouldn't fit within the observable universe. So QI predicts a minimum acceleration for the universe that cannot be, you can't go below that.
Okay, I'm thinking of there's now another issue comes in my mind where if the apparent gravitational effect depends on the allowable Unruh wavelength that we can fit between ourselves and this apparent horizon, that doesn't sound that sounds like it depends on just how close that horizon is to us as an observer. It doesn't actually sound like it depends on how much mass there is. So whether it's a plate or a star, it would similarly limit the allowable Unruh modes. But what we observe is your force depends on the mass of this thing over here. And that has this, 1 over r squared dependence, right? But so how is there this mass dependence in that sense versus just this distance dependence?
Yeah, so it depends on how many Planck masses you have in the star. So the more you have, the more it damps the Unruh field.
Okay. So it's the availability of these Planck masses. So like each Planck mass can do some amount of shielding.
Yes.
Okay.
So I've done the calculation, and as you say, it doesn't work. It only works if you assume that it's every Planck mass contributes to the effect at the scale of the Planck mass. You can't do it at the scale of 2 Planck masses or half a Planck mass. It has to be a Planck mass. But it does work that way.
Mm-hmm.
And a Planck mass is quite an annoying mass because it's much larger than an electron mass, for example. It's about the mass of a flea's egg or something like that. It's 10 to the minus 8 kilograms. So it's not that small. But it's the mass at which quantum effects become important.
So is that trying to imply that things smaller than that Planck mass, which may correspond to physical objects, it's not like Planck time, which is like the smallest discernible unit of time interval, but this Planck mass, things below that would not have a shielding effect and so should not provide any kind of apparent gravitational force?
Yes, I said that in the paper I published. The physics should be different for objects less than that. I don't know what that means in terms of things you can observe yet, but masses less than that should not have a gravitational effect if they're by themselves.
Okay, that seems interesting because I think, I mean, haven't we measured like the mass of a proton and the mass of an electron and these kinds of things?
We've measured I guess we've measured the inertial mass, but I'm not sure whether we've measured the gravitational mass,
Hmm.
because
So
that
it's
would be
okay.
would be different.
Okay. So in this model, there's a cutoff for gravitational mass.
Yeah. So I think in the paper I
Yeah.
said that there should be a lot of space dust at a certain scale because of this effect.
Okay. Okay. Now I'm going to keep pushing for this. How do we solve this cosmological inflation problem now? Because this looks like space is
Yeah.
expanding at an increasing pace, right?
Yes. Okay. So this is cosmic acceleration and dark energy. So this explains that. And then, well, to answer your question, I can go a bit further. Mass is not there, but okay. So the mass is okay on this slide, although there's a few defects up there. So there is a problem with cosmic flatness. So it turns out that the cosmic potential energy is about the same as its kinetic energy. The cosmos is flat, and so people like Alan Guth proposed the early inflation of the cosmos, a huge amount of acceleration early on, so that it would be flat now. This kind of condition where the potential energy is equal to the kinetic energy looks very much like a coincidence of the current epoch in the current model as well. And this was pointed out by Unziger 2008. But in QI, the model is that in any volume you have, the acceleration must be high enough that Unruh waves become short enough to fit in it. So I've kind of shown that with this yin-yang diagram here. You can see the circle with a curve in it. So the circle is the cosmic horizon, of course. The mass in the center, the black dot, must be large enough that the Unruh wave it sees, so the wave shown there, is shorter than the cosmos. So the way you write this mathematically is that and I've shown it in the center, that the gravitational acceleration, gm over r squared, has got to be greater or equal to the minimum acceleration predicted by quantized inertia, this 2c squared over theta. So, and what you do then is you realize that theta is 2r, just 2 times the radius, diameter. And then you get the formula below at the bottom, which is just potential energy equals kinetic energy. So if you put an extra mass in there, you'll see that it's the same. So this predicts that potential energy is always going to be equal to kinetic energy through all epochs. And it gets rid of the need for inflation because it predicts that the universe is going to be flat. So yeah, I guess that's my answer to your question about inflation.
Does this, how do we get to, does this now say that the universe may not be expanding? Or how do we get to, because we have this like big
Yes.
bang cosmology where things have expanded to a great extent. Is this now we have like sort of a fixed speed of expansion that's not speeding up in time?
Well, I wasn't going to go into it in the talk, but what quantized inertia seems to suggest is that the universe is not expanding, but the higher redshifts we see for more distant objects is because we're looking at them in the past, and in the past the cosmos was smaller. Informationally, it was smaller. So that means that the physics, according to quantized inertia, the physics will be slightly different because it depends on this theta value there. So for one thing, galaxies in the early universe must have spun more rapidly. Also, electrons in atoms would have had less inertial mass. So with an atomic transition, they would release less energy. So there would be a redshift. And I think this is what accounts for the redshift that we see with distance and not expansion. And I can prove what I said about early galaxies spinning more rapidly because I've tested that.
Sorry, hold on, because you said something that maybe I misunderstood, but you said that we don't need an expanding universe in this model. But then you've also said that in the past, the universe was smaller. So those
That's
two
right.
things don't seem to square with each other, because if the
Yeah.
universe was smaller in the past, the smaller than it is now, at some point it must have expanded.
Yeah, that's a very good point. And what I'm saying is that in the past, the universe was informationally smaller. So the amount of volume of universe we could have got information from in the past is less than it is today. Was less than it is today. So I'm saying that physically it's not expanding, but informationally it is, and it's the informational size that is important in quantized inertia to change the physics.
What do you mean when you say information there? Because I thought information was conserved, and I thought this conservation of information plays a role into the construction of like a Rindler horizon, where because information is conserved, then we have the apparent production of heat on this Rindler horizon. And so you're saying that the overall information content of the universe is increasing in time?
Yes, that's right. I'm saying that information is not conserved. Some physicists think it is, but I'm saying it isn't. And so when you delete some information, you get heat out, and that accounts for the UNO radiation. I suppose if the universe is expanding, you'd have the opposite. Right.
Okay, I think I'm kind of following here. I feel like there's something here where saying that information is not conserved I mean, there's two sort of conceptions of this that I think often get conflated, and it's the difference between fine-grained entropy and coarse-grained entropy, right? So fine-grained entropy is the total information description of a physical system. Now, this is conserved in time in the sense that physical laws are time reversible. But that assumes that you can distinguish between any two possible microstates, even if to a macroscopic observer they appear indistinguishable. That's the kind of information that's conserved. Now, the second concept of coarse-grained entropy is that is entropy is increasing over time, and that's because of the indistinguishability of these microstates. And so second law of thermodynamics looks like entropy is increasing over time, looks like accessible information is disappearing in time in some sense. It's all turning, in the limit, it's all falling into black holes and getting evaporated as Hawking radiation or something like that. Are you saying here in the this fine-grained sense of information, is that the full information description of the universe, this kind of information is increasing in time?
Well, I'm not familiar with the fine-grained and coarse-grained that you're talking about. The way I model
What's the difference between von Neumann entropy and Gibbs entropy?
Okay, well, what I'm using for information is simply I'm counting the bits as a Planck length of space. So I'm assuming that each Planck length of space is 1 bit. So as the cosmos expands, our access to information increases in that way.
You're saying the cosmos is expanding, but just earlier you said that you don't need to have an expanding universe with quantized inertia to explain the redshift of distant stars. But now you're saying the cosmos is expanding. So I'm trying to square these two things. How do we have?
It's not physically expanding, but it's informationally expanding. So we can see more of it, but things are not moving away from each other.
So you're saying it's not spatially expanding, but you've also said that what you count as 1 bit of information is 1 Planck length or 1 Planck volume of space. And so if that information content is expanding, then you think that there's more space, unless you're saying that the Planck constant itself is changing in time.
I suppose maybe the difficulty is that I'm saying that masses are not moving away from each other. So everything is static. It's like a steady state universe. But the amount of it we can see is the catchment area of light is always increasing. So the cosmic horizon is always increasing. So in that sense, the universe is expanding.
Okay. Okay, so it's like our sphere of causal influence is expanding with time because of the finite propagation of light. And so the informational content that we can couple with as observers or become entangled with in this quantum mechanical sense, that is expanding in time just by dint of being an observer that has an expanding kind of light cone or something like that, or
Yes.
causal sphere of influence.
Yes, it's like that.
Okay, I think I can kind of get that. Okay, so it's okay. So we kind of have. I mean, I think the answer for the dark matter galactic rotation curves was clear to me. I think we have a second kind of arrow in the quiver here, which is providing an alternative explanation for the apparent increasing redshift of distant galaxies and or distant supernova, and saying that's not necessarily because of the spatial expansion. It's because of this expanding sphere of causal influence, which means that we have more information that can interact with our current position in the universe,
Yes.
and that this could produce what looks like an expanding universe, but it's because of this information content of our sphere of interaction expanding.
Yeah.
Okay.
Yeah.
Okay. I think I'm getting that. So now I'm really curious about your work and kind of experimentally verifying this or proposing experiments, because I think, I mean, the catchy thing on the first slide was this reactionless thruster, and how could we use quantized inertia to have non-Newtonian propulsion. And for people listening, I mean, why that's a big deal is because we live under the tyranny of the rocket equation, right? Where we have to carry fuel with our spaceships into orbit, and this is a huge deal. So the refueling issue is massive, but also it's like, how do we have enough Newtonian mass to get to distant stars? It's very difficult. Like ideas like Broussard-Ram scoop and stuff like that, we have to scoop up interstellar hydrogen and fuse it. It's very difficult. It's very difficult. So if we had just something that could produce thrust from just electrical power indefinitely, then we could actually get to like this constant acceleration and, you know, travel to the center of the galaxy in like a few years of shipboard time or something like that.
Yeah. All right. Well, I'll skip on to that bit then. So I was just going to show you more evidence that past galaxies spin more rapidly, but I can. Oh yes, and the gravitational constant is also predicted by the theory, but.
Well, hold on. How do we get that? That sounds interesting.
Right. So, well, shown here, although there's a defect on the equations. Sorry about that. Something to do with SteamYard, I guess. So as I showed you before, because quantized inertia has to keep unrelated radiation shorter than the cosmic horizon, you get this formula: Gm over r is c squared. Potential energy is equal to kinetic energy. And if you invert that, of course, you just get G as c squared theta over 2 times the mass of the universe. And it's been known for some time that this equation works. If you put the values in, you get G within certain uncertainties. And this was known to Dirac, Sciama as well a long time ago. But QI gives a reason for it. You can actually derive this relation from this idea of ensuring unruh waves are short enough to be observable. That's all you need to get that formula, and it means you can predict G. So instead of all our formula in physics that use G, we can now put in c squared, theta, and the mass of the universe, which are known quantities. We don't have to just use an arbitrary constant anymore. So that simplifies physics, and it also implies that G depends on these things. So what would happen if we changed the size of a cavity, for example, or changed the speed of light? Would G be different? Can we control G? So I guess that leads quite nicely onto the propulsion bit.
Now, in this, I mean, we expect G to be a constant in time. And so theta here is kind of the observable diameter of the universe, defined, as you said, in this kind of information sense. And now for that to be constant, then the mass m sub v should also increase proportionally to this increase in theta.
But would G be constant? There's no... I mean, G may vary. I mean, the problem I'm having at the moment is which one of those, or any of them, are constant. Is there any reason why anything should be constant? So at the moment, I'm assuming that none of them are constant.
And m in this equation, is this gravitational mass content, or is this like the mass energy content to the universe?
Yes, that's right. Yeah, so that will increase. Theta will increase. The speed of light will either have to accelerate or decelerate. I'm not sure which one fits. And G may vary as well, but there are certain bits of data that that I'm getting that might help me to test this formula backwards in time. There's things like the faint young sun paradox. I mean, the sun was supposed to be dimmer in the past, but it appears not to have been dimmer, which is puzzling to standard physics. So could it be that, you know, G was greater back then, and the fusion reactions were stronger because the sun was being compressed more? And the Earth may also have been smaller, that kind of thing. So this sort of thing can be tested.
Okay. And how would we test this?
Well, so I've started doing it by looking at ancient galaxies. I mean, I just skipped over the slide actually, but I was going to show you the little red dots which have just been seen by the James Webb Space Telescope. They're galaxies very far off redshift 5, only 1 billion years after the Big Bang, and they're rotating incredibly fast, which is just what is predicted by quantized inertia. But in order to predict it correctly, you have to realize that the mass of the universe back then was less because it was smaller, and the size of it was smaller, obviously, so theta is different. But if you assume all that and those changes, then you get the correct prediction for these little red dots. And I haven't published that yet, but and unfortunately you can't see the equations here because of the software, but it predicts it accurately. It predicts the right value, so 1300 instead of 1500, but it's within the uncertainty. So that's one test for this.
Yeah, there's something interesting here that's kind of not, I mean, I haven't quite grokked it completely, where we say the universe was smaller in the past, but what you really mean was like the causal sphere of influence from the finite propagation of speed of light had a smaller volume under consideration. But the this means that basically where an observer is located in the universe, like if I was closer to those distant galaxies, they would be less in the past. And so I would be observing them having a different kind of formation pathway than someone where I am.
Yes, it would be less red.
Right. Okay, I think there's some open questions there, but we can.
Yeah.
I'll have to do some reading and think about this on my own. Yeah, let's continue here with the I think the reactionless drive.
The propulsion. Okay. So if dynamics is due to quantized inertia, and I think I've shown enough evidence for that, we can use it. So what you could do is you could have a highly accelerated core. So I've shown that in this square in the center, where you've got an object spinning very rapidly. You've got to spin it incredibly rapidly so that the Unruh waves shorten, because the faster the acceleration, the shorter the Unruh waves. And if you get them short enough, so a few centimeters or so, then they will be dampable by a metal plate because they will interact with a metal plate. So very long electromagnetic waves can penetrate metal or the ocean, for example. But if they're about the same size as a damper, they are damped by it. So that would mean that you'd see this spinning object would see Unruh waves coming from all directions, from below, from the side, but the Unruh waves coming from above will be damped. So that would mean there'd be a push from below upwards. So this would produce a kind of levitation. And it would be a thrust which is propellantless or reactionless, because you're just putting energy in to spin it, electrical energy, for example, or it could be a capacitor with highly accelerating electrons. You're not using fuel, and yet you're getting some thrust. So I talked about this first in a paper in 2013, but the main paper was 2017. And I was contacted by DARPA and awarded 1.3 million to try and demonstrate this in the lab. So the first thing to do was decide how to do this. Well, there are many ways you could potentially do this. So on the left, we have a capacitor, so that you can see the two black rectangles there, the anode on the left. Electrons highly accelerated across the gap, see short under waves. And what that should mean is that well, I'll show you on a later slide. It doesn't seem to have come out well here, but it should mean that under waves are damped between the plates. So the electrons will lose inertial mass. And in order to conserve momentum, the capacitor has to thrust towards the anode. And in fact, anodes thrusting in this strange way has been seen since before the 1950s by T.T. Brown.
Yeah, Thomas Thompson Brown, Townsend Brown, the Townsend Brown effect. Yeah, yeah,
that's right. Yeah,
yeah,
yes. So,
that experiment relied on having, I think, an asymmetrical shape for these capacitor electrodes. And if you had normal parallel plate electrode, you would not see this. And I think a lot of people since then have tried, explain this as, oh, it was just ionic wind. It was just the creation of charged like atmospheric gases that would then get accelerated downwards. And so it's really still Newtonian propulsion. There's a new startup, though, actually, I think based in Florida, founded by this fellow who used to be he was the head of NASA's Applied Electrostatics Library. I forget the name of the startup just at this moment, but
it's Exodus Technologies, I think, and it's Charles Bueller.
Yeah, Charles. Yeah, that's right.
I'll show you some of his results in a minute. Yeah.
Okay. Great. Yeah.
Yeah. So, and then the second one. So this was a very controversial one. Russian Podkletnov. He had a superconducting disk, and he span it very rapidly. And this particular disk had smaller crystal grain on the upper surface than the lower surface, which I've tried to show there with the different pixelation of the solid. So a finer crystal in the upper part of the superconducting disk that's rotating should damp under waves more than the crystal below. So, and I've shown that with the rectangle below, you should have a lot of under waves below and fewer above. So there should be a push upwards. And in fact, Podkletnov did see a push upwards. Then there's the M drive, which is also very controversial. So this was a copper cone built by Scheuer about 2001 or somewhere around that time. And he used a magnetron to put microwaves in, resonate them in the cone, and he found a push towards the narrow end. Well, I found that I can predict this also very well with quantized inertia, because the narrow end of the cone damps more under waves than the wide end does. So you can see the rectangle below, there's blue on the left and a warmer color on the right. So you should get a push towards the narrow end, and you do. That's what he saw. And I found that I could predict his thrust incredibly well. And also I could predict a change even when he put dielectrics in one end or the other. So I wrote a paper or two on that. And then there's also James Woodward, who had capacitors that were vibrated by piezoelectrics, and they had a thick plate on one side, so on the left, as you were saying earlier, and a thin plate on the right-hand side, as you can see on the right-hand side there. And the thick plate will damp the under waves more, so you get the blue color below, and the thin plate will damp them less, so you'll have, again, a gradient pushing left, and indeed they push towards their thick end. So the common factor in all these is you need an incredibly high acceleration so that the under waves are short enough to become tractable, to become interactable, and you need asymmetry of some kind. So a capacitor, it's movement of the electrons in one direction. With a Podkletnov disk, it's a difference in crystal size. With Scheuer's cone, it's obvious it's the asymmetry there. And in Woodward, it was the change in the thickness of the plates. So as long as you have these two, high acceleration and asymmetry, you should be able to get some thrust. So I started the DARPA project, and two people from California, Frank Becker and Anke Bat, read my papers, and they wanted to try a capacitor setup that Frank Becker had some experience in. And so they, this was the beginning experiment. So they put a capacitor shown sort of in the center in the red circle on a digital scale. It had a cathode, an anode, and a dielectric of Kapton or PTFE, some kind of plastic in the center. It varied. It was sometimes Kapton, sometimes PTFE. They put about 5 kilovolts across it. That varied too, and they got about 10 microamps of leakage current from the cathode to the anode. Quite a small current, but they saw a thrust of up to about 6 millinewtons pushing up towards the anode, which is very similar to the result of T.T. Brown, but their test was better and I guess simpler. And I found that I could predict what they were seeing. So this graph here shows the separation between the two capacitor plates on the x-axis. So on the far right, we have about 120 micron separation. And then on the far left, we get down to about a value. A diamond shape is on about the 10 micron separation. And you can see that as you go to smaller separations towards the left, the thrust they saw, which is the black diamonds, increases exponentially. And the force is shown on the left, and it gets up to about 6 millinewtons. So 6 times 10 to the minus 3 newtons. So it depends very much on the, it depends on the 1 over the separation squared. And the formula on the upper right is the QI prediction of quantized inertia for the thrust from this capacitor, assuming I'll go into it intuitively in a minute, but that's the formula. And you can see the force is proportional to a lot of complex things, but divided by d squared. And when you apply it to the data, it predicts it exactly. It's shown by the prediction shown by the squares, the open squares. And you can see it agrees perfectly with the data that they saw. So I published that in a paper on, I think that's only on ResearchGate, that paper, but you can see it there.
And this was measured in a vacuum. So this is ruling out any kind of ionic wind effects just via the ionization of gas particles and accelerating towards one electrode.
Some of these tests are in a vacuum. This one was sometimes in a vacuum and sometimes not. They used a vacuum bag, which is not the best kind of vacuum. So,
I mean, that would seem like a pretty important confounding variable here, and it's something that's historically been used to debunk fully the Thompson-Townsend.
Yeah.
Thomas-Townsend.
But they did encase the capacitor. So the capacitor was encased in a Kapton shell, if you like. So there's no way that the ion drift was touching the plates. But it's true that there could have been an ion drift outside the Kapton shield, if you like. But I'll show you a corroboration by, well, I'll come back to that in a minute.
Sure.
There was a test in vacuum as well that I'm about to show you. So the explanation for this is shown here, the way I've modeled it with quantized inertia. So normally the top rectangle shows an electron moving along happily in empty space. So it sees more onward radiation in front and less behind, because there's that Rindler horizon damping it behind. So it feels inertial mass. But between the capacitor plates, and again, the colors have come out a bit funny, but the capacitor plates effectively get rid of the onward waves. They damp them. So the normal mechanism of inertial mass doesn't work. So there's a problem with conservation of momentum there. So the system has to push the capacitor in the direction of the anode to conserve momentum, because the electrons have lost theirs. So if you assume that, you can predict the thrusts, these thrusts. So yeah, I'd encourage people to read the paper, which is on ResearchGate. And then Becker and Batt also did this very interesting test. So this shows the capacitor in sort of the center here, with the electrons accelerating to the right, to the anode. And and I sent them a prediction of the expected Rindler horizon, where it was going to be. It was something like a centimeter away or something like that. or a few centimeters, perhaps. Yes, about 6 centimeters. And then he tried an experiment. They held a metal baffle behind the electrons to influence them, and it did, as shown by that picture. But as soon as they moved the metal baffle behind the electrons within the horizon, then the effect of the baffle on the electrons stopped, which meant that the electrons could no longer see the metal baffle, the metal object.
Okay, so you're showing that the induced lunar horizon from acceleration, if you create a new horizon closer than that, then you'll see an additional thrust as you'd expect with this quantized inertia model.
Yeah, well, when it was closer than the horizon, the prediction was quite complicated. But the important thing in this particular test was that as soon as you moved it behind this abstract horizon, it had a real physical effect in that the electrons noticed that the baffle had gone because they couldn't see it anymore.
Okay.
So, yeah, that was quite a nice test because these Rindle horizons sound like abstract concepts, but my point with quantized inertia is that they're not, and they have a real effect on nature. And this is kind of the best illustration of that.
Okay, so okay, another experimental verification here.
So this is the vacuum one. So this is to make you happy.
Sure, yeah.
So this test by Becker and Batt was seconded by Richard Mansell with his company Ivo in Virginia. And they made some improvements, of course. They tested it in a vacuum, and you can see on the right, their plates, their capacitor plates, which are stacked together in a vacuum chamber, which was at E Labs in Fredericksburg, Virginia. And they also used a pendulum, not a digital balance, to avoid electronic artifacts. So they dangled the capacitor on a pendulum and then looked at movements of the pendulum. And they confirmed Becker and Batt's experimental results. They got essentially the same thing. And they had a better design, actually. They had a better dielectric, which wasn't plastic. It was far more robust, which is important for this technology. So, yeah, we were very pleased about that. So that was encouraging. And then I did the same thing at Plymouth. So we set up a test site as well at Plymouth, which is where I was as a lecturer, of course. So we had our capacitor, but we didn't use a vacuum, actually. But I just wanted to show that we did it as well. We had a shield cage. We had our capacitor in the center here. We had a high potential tester charging it up. We had a digital balance. And we also measured thrust, as expected by quantized inertia. And that's our setup, just to prove it was there. And that's my chief engineer, Richard Arundel, standing by it. Okay. So far, there have been 6 labs have reproduced this. So this test shows that. So Becker and Batt, of course, 2018, their observed thrust was 6 millinewtons and QI predicted 5.7. Ivo in a vacuum got 6 and QI predicted 5.25 for that one. So that's within the error bar. We at Plymouth, we got a much lower thrust, but it's within, it's as expected. So we predicted 0.25 and we got about 0.25. And we had a much lower thrust because we were less expert perhaps in manufacturing capacitors than the company in Becker and Batt. Frank Becker is an expert in this kind of thing. And then there was a test done, very nice test, elegant, done in Italy, and they got a thrust similar to ours, actually quite low, but it was as predicted by QI. And then Charles Bueller's test. So I looked at the data he published on YouTube, and he published one of his experiments, and I applied QI to that, and I predicted 5.3 millinewtons, and he observed in that test 4.5. So I think he was essentially doing the same thing, But instead of having a capacitor, he had a metal plate with a dielectric on it, and then he oscillated the electrons up and down on that, which is interesting. But you can apply QI to it, and I did, and it predicted it very well. And then there was a test done in California as well, and their results were slightly mixed. You can see that the predicted thrust was 8.5, and he only got 3.5. So, but then Ivo, this company, decided to launch into space, launch a CubeSat with a capacitor on it into space. So we're expecting 1.75 million newtons from that. And yeah, so they did that. So they made their CubeSat. They launched it back in March. It was a SpaceX launch and a Rogue Space Systems CubeSat, Falcon 9, as you can see there. And yeah, they had a few engineering problems, and I can't tell you exactly what they were, but they were only able to fire the thruster for a certain amount of time. So they were very limited in the thrust they could produce. But I've looked at it anyway, and what I've looked at is the height of the satellite compared with another CubeSat that's identical in shape and was launched by the same rocket, so it's at the same height. So this table here, top right, shows the second row there is the Ivo satellite 63235, and its original height, well, 3 months ago, was 506.3 kilometers low Earth orbit, and very recently it had fallen to 501.42, so it had fallen about 4.88 kilometers. The other one, it was identical, had fallen a bit less, sorry, a bit more, 5.48 kilometers. So it seems that the Ivo satellite fell 600 meters less over 3 months. So does that equate to what their thrust could have been? Well, again, the maths isn't visible on this. Sorry about that. But what I can say is that if taking into account the limitations they had and working out how much they could fire every day, then they should have made a difference of about 5 or so meters per day over the other satellite. And the actual difference between the two satellites was an observed rise of 6.6 meters per day. So that's kind of encouraging. But of course, unfortunately, it's not conclusive. We were hoping for a much larger thrust.
Does that order of magnitude, like if you work out what the change in momentum would have been to get this increased orbital altitude, does this correspond with how long the QI thruster was in operation or its total power consumption? Was there some alignment there?
Yes, it does. So what I've done is yeah, I don't suppose I'm releasing any secrets if I say they can only fire it for a minute every certain time period.
Right.
And I've taken that into account to calculate how much that would produce as thrust, and then how much that would raise the satellite. The equations should be here, but they're not. And you get 5 meters, and
I'll pause to emphasize the importance of that. If it is, I mean, if it is the result you're claiming, and it sounds like there's various reasons to suppose there's an effect here. The effective lifetime for satellite missions is limited by their onboard propellant, right? For station keeping, avoidance, maneuvering, avoiding collisions, like maintaining against orbital drag. And so, people spend tens of millions of dollars on these satellites, put them in orbit, and they have a finite shelf life because they just run out of propellant. And I mean, right now, mostly it's ion or Hall effect based thrusters, right, that produce very small amounts of thrust over long periods of time, mainly just consuming electrical energy, but also consuming gas that they accelerate through an electric field to produce the thrust. So I mean, the interesting thing here really is that if you could have if this effect operates purely just by electrical consumption, then you can have kind of an infinite duration satellite mission lifetime, even in low Earth orbit, where it experiences atmospheric drag by producing this kind of counteracting force that doesn't consume any propellant.
That's right. Yes. Yeah. That's the great thing about it. Yeah. And I've got a slide on that sort of thing here. So if you look at the Dawn probe, which had an ion drive, and it was that went to Ceres in the asteroid belt. So its ion drive produced about 90 millinewtons of thrust from propellant by expelling propellant. I guess it was xenon or something. I'm not sure exactly. But the problem was that the weight of the propellant was about half a ton, 434 kilograms. And it needed about 2 kilowatts of power to do all that. But the main problem was the propellant, which means that when you work out the acceleration, so it's F divided by the mass, you get a huge mass to slow you down. So they can get from 0 to 60 miles an hour with this ion drive in about 1 or 2 days, which is okay for what they're doing in deep space. But with the kind of thrusts we're already seeing in the lab, for example, on the CubeSat, a QI drive might produce about 1.75 millinewtons, something like that. That's what the IVO one was supposed to be producing, which is it's very small. It's about the weight of a paperclip. But the great thing is that the weight is only 3 kilograms. So all you've got is the CubeSat, and you're getting the energy from the solar panels. So the acceleration is much higher because it's F over m. M is small, so the acceleration is large. So you can accelerate from 0 to 60 miles an hour in half a day. So it's much better simply because, even though it's weaker, because it's got no fuel, as you were saying. So that kind of quantifies it.
Mm-hmm. The figure of merit for propulsion systems is the specific impulse, right? Which is like, how many seconds can you produce 1 pound of thrust for 1 pound of fuel, which kind of mixes units of mass and force, but whatever. Yeah. But this would have a specific impulse of infinity because there's no propellant consumption.
Yeah, people have asked me to calculate that, and I always tell them it's infinite. So
yeah.
So yeah, it's definitely an advantage, a huge advantage there.
Yeah. So these things all came to mind. It's basically anti-gravity in some sense, not in this conspiratorial sense, but in the sense that we can produce gravitational-like effects just using electrical power.
Yes, that's right. Yeah, that's what it's doing. So the applications are obvious. Satellite station keeping is the first obvious one, which is what IVO were going for, of course. You've got lighter satellites to launch. They don't need to carry fuel. Obviously, flying cars. I think there are several ways to hugely magnify this thrust that I'll hint at a bit later. But I think we can have flying cars, that kind of thing, and even structures that hover. And in that regard, Paul Kletnov was a bit of a clue, because I think we can make a structure that has a different grain of cavity below and above, and that will damp Unruh radiation more, create a great vertical gradient in the Unruh radiation, and thrust it up. So you could have self-thrusting materials, which would be very, very useful. Mm-hmm. I think eventually we'll be able to launch with this sort of thing, a quantum launch system. Also, inertial dampening I've listed there. The great thing about this is that if you're on a rocket and you fire your rocket, you get pushed back into towards the back of the rocket. And if you want to accelerate hugely, then you get crushed, which is a problem. But with a quantized inertia propulsion system, you could accelerate at any acceleration, and you wouldn't get crushed, because the way it works is it's almost redefining inertia itself. The gradient in Unruh radiation works equally on every part of the structure. So the passenger would be accelerated by the same amount as the ship. So there'd be no pushback, there'd be no whiplash.
That's if the passenger was somehow like inside this cavity, right? Like they would have to be on the cavity is the exterior of the hull, I guess. Because if it was a small drive just inside pushing, you'd feel the conventional acceleration forces.
Yes, that's right. It'd have to be embedded in a hull or something like that.
Right. This is interesting. Well, I mean, this is like $1 trillion idea or technical breakthrough in my estimation. I mean, if it works, I'm saying there's evidence for it that you've presented quite clearly. And I think, yes, I'm curious then, where do you intend to take this next? I mean, is this something that is sort of at the stage of sort of commercialization, or is there still some more experimental work to do? I'm curious what's next on your roadmap.
Yeah, so I can skip ahead to that. So, yeah, the best test thing I'd like to do next, apart from developing the theory more, which I'm doing anyway, the best tests would be, well, space tests are difficult because you can never be sure that the electronics is going to work, the engineering is going to be right. The best way to do it would be to do it on a lab bench and enhance the thrust. So I've shown a picture here of a cube kind of levitating off the desk. That would be a result which would convince people, I think, because they could come in, they could see it levitating, they could wave their hands around and check there's no trickery involved, and then eventually we could launch something. And I think there are ways to do this. An obvious way to enhance the thrust would be to bring the capacitor plates further together. You saw how the thrust was increasing exponentially as you brought them together. The only problem is if you bring them closer than about 8 micron, the electrons start leaking across instead of jumping, quantum tunneling across, which is not what we need. We'd need a much stronger dielectric. And I haven't identified one yet, but if that could be identified, that would be a way to go. And there's another way to do it that we actually tested in the lab in Plymouth that I'd like to try, a way to enhance the thrust by about a factor of 10, which I'd like to try. So that's what I want to do next, try to levitate something. So there are some people who are thinking of funding this, and so it may happen, but of course nothing's been promised yet.
Yeah. Well, I mean, in the sense of like sort of, if only capital were to flow along like a constant curve and expectation value of what the impact could be, that there should be a lot more funding going to this kind of thing than there is currently. Because I mean, if it works, it revolutionizes the space industry. It revolutionizes how we do station keeping for satellites. It opens up new forms of not just interplanetary transit, but also interstellar travel, which is kind of the Star Trek future. So I think that's what we're all kind of hoping for.
Yes, it does. And what I'd like to end with really is an Oort cloud or interstellar mission, because, as you say, the problem with getting to the nearest star is that to get to half the speed of light, to do it in a human lifetime, you need to have massive amounts of fuel. So it becomes an engineering impossibility. But this propulsion system has no need for fuel, just power. So we could, normally it would take a rocket 500 years to get to the Oort cloud at sort of 2000 AU out. It would take a quantized inertia drive about a year. So it'd be nice to try that, see if the Oort cloud is really there. And then it would just move on to Proxima Centauri. And I think that would be doable in 10 to 15 years. With rockets, it would take 70,000 years to get to Proxima Centauri. So this is the way to do it. We could send a probe, and here's a picture of the probe arriving at Proxima Centauri.
That's 10 to 15 years from our proper time frame of reference. That's us observing the probe. That's not saying it's a relativistic time dilation on board where it takes less time. I mean, that effect would also occur, but
yes, that effect is there, but it's quite small. It's, what would it be, a year or two in difference? So we could get a signal by 2050 if we did this.
I mean, it's fantastic. I would love to see this. This is where's the GoFundMe? How do people invest in this concept? I guess is there a corporate entity? Is there some kind of like foundation or institute? I mean, how can basically, for the people watching, there's now 1,300 people watching live, but how can people help support this kind of experimental work and help kind of potentially revolutionize the space industry?
Well, the proposal I have is to set up a Horizon Institute. So this is kind of the plan. Set up a Horizon Institute, which involves a combination of theory and lab, so next door to each other, where I would try to apply the theory and the lab would do these tests, try to levitate something and then launch it. And the cost per annum, I reckon, will be about 400K. So we'd set it up for 3 years, and at the end we should be able to demonstrate this levitation. And I've also mentioned energy harvesting, but that's a different issue, but I think that's also possible. So we could demonstrate levitation, demonstrate energy harvesting. and then we could move on to building and launching a probe to the Oort cloud and Proxima Centauri after 2030, which would take maybe 5 years to build. I mean, it doesn't have to be large, but it would have to have a decent dish to send images back. And we may need to have more than one probe because to form a chain to get the message back. And as I said, we can get the images back from Proxima by 2050. So I have been trying to set up a Horizon Institute, and I'm obviously on email. So if anybody wants to contact me, they can look at my university email address or my Gmail, which is shown there. And I've also described all this in my book, which is Quantized Accelerations, here, so you could read that. And there's also my Patreon. I said I'm crowdfunded, so if you're interested in supporting this work, please go to my Patreon site, which is this patreon.com, one step to Tau Ceti there. So that's kind of my conclusion slide.
That's awesome. Yeah, I highly encourage everyone watching that's interested to reach out to learn more. And I would also humbly suggest there's a column missing from that table, which was the massive amount of revenue you could be generating by selling these as onboard propulsion systems to the satellite market. I mean, that by itself, you'd be self-funded in perpetuity after that point.
Yes, that's probably true. Although I'm not a businessman, I'm a scientist, so it's.
Well, business acumen is in far greater supply than novel scientific insight, and so that would not be the hard part. I think if you prove out the certain level of like technological readiness level here, and saying that this is a consistent, demonstrable benchtop experiment that can work, I think then thinking there would be no shortage of capital. I think that would be willing to invest into a venture proposing, hey, let's capture the entire satellite propulsion market with this kind of thing, and then I mean, then it becomes profitable as well to get out there, to start exploring the Oort cloud and these kinds of things.
Yes, that'd be great. Yeah,
that'd be great. Cool. Well, thanks so much, Mike. Thanks for joining. I really appreciate you taking time to present on this. It's a very interesting topic, and I'm sure we'll see more as you kind of continue to flesh out the experimental results. And yeah, I think this is great work that deserves to be funded. And I mean, even if it's the 1% chance that it's all correct, and I think you've shown probably a higher % chance there's something here, even that should justify, I think, a good deal of investigation and technical efforts to prove it out.
Well, yeah, thanks so much, and thanks for inviting me. I've enjoyed it. So.
All right, thanks so much. And you're also on Twitter too, so we'll see you around. Okay, well, I will just wrap it up there. Thanks so much, Mike. Awesome. Cool. All right, that was great. Thanks so much for joining, everyone. That was Hyperstition number 7, Quantized Inertia. It takes a lot of guts, I think, to challenge the prevailing orthodoxy in physics, especially something like Einstein's general relativity, which is reigned supreme for almost 100 years, actually. So tomorrow's talk, we're going to revisit Bell's theorem. Last week we had Richard Behill on talking about Bell's theorem and the concepts of local realism, getting into whether physical reality exists independent of direct observation, which is a very spooky thing. And I mean, Richard Behill, he's a pretty pragmatic experimental physicist and engineer, and he came away with some disquieting conclusions on that. And tomorrow's guest is going to be kind of a reaction to that talk and that presentation. It's going to be with a new friend, Benelli Dereshani, also known as Max. Max is a professor, or he's a researcher in theoretical mathematical physics at the Stony Brook University in New York. And he's going to join us to kind of explain. He's also a member of this thing called Bell's Institute, which is all about interpretations of quantum mechanics and how it relates to our ontology. So I hope you can join us then. That'll be at 1 p.m. PST. Thanks so much.